Thank you for joining us today. I'm Wes Walker. Our topic is organizing an inline FTIR implementation using ACEs, Application, Communication, Environment, and Sampling. Today we will focus on Part 1, Applications and Communication. Introduction to ACEs. Let's break the implementation into 4 parts. 1. Application. This is the part composed primarily of molecules, spectra, and manipulation of spectral data. A common example is a prediction of the concentration of starting material as a batch reaction nears its endpoint. 2. Communication. Once the spectrum is collected, it will next be transferred to a PC, likely in a safe area. How will we make the connection? Once the spectrum has been processed, will a trend value need to be read via Modbus or OPC by a control system? In Part 2, we will discuss environment and sampling. Hardware. Let's look at some features of the hardware, beginning with number 1, which is the main spectrometer body. It's housed in a NEMA 4X enclosure. The overall height of the instrument with frame is 76 centimeters or 30 inches. The optical interface module, number 2, allows the user to plug in fiber sampling technologies. With the OIM removed, mirror conduits can be used. Number 3 is a silver halide fiber with an integrated RTD. It is available with a diamond, silicon, or cubic zirconia sensor. Number 4 is the Expo Mini Purge. It automatically removes power from the instrument if purge pressure is compromised. Number 5 is a stainless steel frame. It can be mounted on tabs or carts. It is also available with wheels. Number 6 is a flow handling unit. This routes dry air or nitrogen to the Expo Mini Purge and cooling fins. Number 7, the cooling fins. These fins conduct heat away from the hot side of a thermoelectric cooling unit. The FTIR 45P has an active temperature control system that will stabilize the unit between ambient temperatures of 32 and 95 degrees F. Applications. What problems can FTIR address? FTIR is often useful for decreasing cycle time, often by the accurate determination of endpoint, monitoring and controlling the accumulation of hazardous intermediates and byproducts, monitor and controlling the formation of impurities or byproducts that result in waste or additional processing steps, and increasing operator safety by reducing or eliminating manual sampling. Application Example 1, Endpoint Determination for Chemical Production. A chemical production process was monitored with FTIR. This allowed shortening of the hold time at the end of the process. The shortened hold time resulted in higher yields due to the elimination of product degradation. Application Example 2, Oxidation Process. This work was published in Organic Process Research and Development in 2004. The title is Development of a Safe and Scalable Oxidation Process for the Preparation of 6-hydroxybuzpyrone. A metabolite of buzzpyrone shows promise to discovery chemists. Multi-kilogram amounts are needed for toxicology, formulation, and clinical trials. Process R&D was challenged with developing a rugged process that could deliver product with reliable quality. A fast determination of endpoint was needed to avoid making the dihydroxy impurity. What were the challenges? First, to monitor the deprotonation of compound 1 for a more precise determination of endpoint to minimize double deprotonation. The process also must allow for variations in the base titer, water content, and phosphide quality. What was observed? The deprotonation was complete within 5 minutes. The enolate anion 3 was stable at minus 25 degrees C for 12 hours. It was unstable at higher temperatures, and the kinetics of degradation were monitored by IR. The trends on the right show how incremental charges of base cause a decrease of starting material and a corresponding increase in enolate. How was the process improved? In step 1, base was charged until complete consumption of the starting material was observed via a stable signal at 1677 wave numbers. In step 2, an excess of 1 to 3% of starting material was introduced. The result? Impurity compound 8 is minimized. Conclusions. The reactor allowed titration of the correct amount of base, which prevented accidental overcharge. It was implemented in the pilot plant, producing 13 kilograms. The need for recrystallization due to impurity was eliminated. In this fed batch fermentation, ethanol is a nutrient storage material and a critical parameter in the process. The top trend shows ethanol over a 40-hour period. Bottom views are overlaid spectra and a 3D surface plot which has been reversed. Glucose is consumed, ethanol is formed, and then finally the ethanol is consumed. The data and model clearly show that FTIR can be used for trending and controlling ethanol concentration. Other species that FTIR is useful for in fermentation include ammonia, lactate, dissolved carbon dioxide, glucose, and essentially all other small organic molecules of interest. FTIR is used for biofuels, nutritional compounds, and active pharmaceutical ingredients. Application example 4, hydrogenation. Product and starting material peaks are shown in the spectra below. The process was scaled up from 2 liters to 1200 liters, and the FTIR was used throughout the project. Now we show the trends for the process. It would be challenging or perhaps even impossible to get these trends without a probe in the reactor. By reducing or even eliminating manual sampling, we've increased user safety. Application example 5. Diisocyanate consumption and prepolymer formation. The peak between 2200 and 2300 corresponds to the diisocyanate, and it can be seen decreasing. The peak between 1700 and 1800 wave numbers corresponds to the prepolymer carbonyl, and it shows an increase over the course of the process. If we turn our attention to the stretching region of the spectrum, we find a prepolymer peak growing and the polyol peak being reduced as the reaction proceeds. In this slide, we see time versus absorbance trends for prepolymer, diisocyanate, and polyol. Application example 6, trending polyol, acid, and ester. In the experiment surface plot shown here, the acid and polyol are shown to decrease while the ester concentration increases. Turning our attention to the trends, we can see the ester peak rising over time and the acid and polyol peaks dropping. Finally, we will discuss communication. Communication. How does spectral data become useful information? First, a spectrum is collected on the FTIR 45P. Then it's transferred to a control PC. If the system is being operated in campaign mode, then the data is displayed and manipulated in the ICIR software package. If the system is being operated in a continuous fashion or connected to a DCS, then the spectrum is analyzed with the IC Process package. ICIR can still be used to view the data even when the FTIR is being controlled by IC Process. Finally, Modbus registers, or OPC UA tags, are readied in the control PC, which is the host, and then they're read by the DCS, which is the client. If we look at the communication setup using optical fiber, on the right in the explosion hazard area, we have the FTIR 45P. Fiber comes into the safe area and connects to a media converter. From the media converter, Cat5 or standard Ethernet cable connects to a PC. The PC can in turn be connected to a DCS. Wireless communication. In the wireless implementation, the FTIR 45P is connected with a short length of fiber to a wireless subscriber. An antenna is used either in the hazardous area or the safe area to bring the signal to the control PC. Software. ICIR is the research side of the FTIR software suite. It is used to view data in real time and produce trends from peak picking, concert, or quantitative models. If IC Process controls the instrument, ICIR can still be used as a viewer, and all of its analysis functions can be employed. IC Process is primarily used for production. IC Process has Modbus TCP and OPC UA communication. Up to 50 process variables can be configured to be read by plant devices.